Introduction to Mitigation Techniques. Module 6, Video 5. Mitigating vulnerabilities is crucial for protecting smart contracts from various types of attacks. Implementing protective security measures ensures the safety and reliability of your smart contracts. Today, we will explore several common techniques used to address these vulnerabilities effectively. Principle of Least Privilege. The principle of least privilege involves granting the minimum permissions necessary for a smart contract to function. This method reduces the potential impact of vulnerabilities by limiting the scope of actions that a compromised contract can execute. By carefully considering the permissions required for each function and avoiding unnecessary privileges, you significantly reduce the attack surface. This practice helps prevent unauthorized actions and mitigate the risk of malicious exploits. In our example, the Solidity code demonstrates the principle. The owner role is empowered to add editors, and only editors can execute the edit function. This access control mechanism ensures that only authorized entities can perform specific action, thus enhancing security. Reentrancy attacks and guards. Reentrancy attacks occur when a contract calls another contract before finishing its own execution, allowing an attacker to manipulate the state of the first contract and potentially causing significant losses. To counter this, a reentrancy guard is used. This mechanism prevents reentrancy attack by ensuring that a contract does not re-enter itself during execution. Typically, this is achieved by using a lock variable that blocks multiple calls to the same function within the same transaction. Our example code shows the implementation of reentrancy guard. The no reentrancy modifier uses a locked variable to prevent reentrancy by ensuring the function can only be called once per transaction, effectively safeguarding against such attacks. CEI pattern. The checks effects interactions pattern is a fundamental security principle for smart contracts. It promotes a structured approach to code execution by separating checks, effects, and interactions into distinct phases. This pattern is crucial for mitigating reentrancy attacks by ensuring that all checks are performed and state changes are made before any external calls. We can prevent an attacker from manipulating the contract state during a reentrancy attack. In this provided code, the contract first validates input and ensures sufficient funds, checks, then modifies the contract state, effects, and finally performs any external calls, interactions. This structured approach significantly enhances contract security. SafeMath library. SafeMath is a library included in the Open Zeppelin library for Solidity. It provides function to perform safe arithmetic operations, preventing overflow and underflow error. These errors can lead to significant vulnerabilities and unexpected behavior. Overflow errors can occur when a calculation exceeds the maximum value a variable can hold, while underflow errors occur when a calculation goes below the minimum value. By using SafeMath, you can handle these errors gracefully, thus preventing security breaches. SafeMath offers numerous benefits. It enhances security by preventing common arithmetic errors, simplifies your code with pre-built functions for safe addition, subtraction, multiplication, and division, and is a best practice for writing reliable and secure smart contracts. Here is an example code. Validate inputs. Input validation is critical for the security of your smart contracts. It protects your contract from malicious inputs and unintended behavior by ensuring that all inputs are within expected ranges and conform to defined formats. Implementing input validation techniques involves checking data types, ranges, and formats to verify the validity of incoming data. By ensuring inputs adhere to these specifications, you can significantly reduce the risk of exploits and vulnerabilities. Our example demonstrates input validation. The function setAge ensures that the input age falls within the valid range of 1 to 150, preventing invalid values from being accepted and protecting the contract from potential errors. Avoiding magic numbers. Magic numbers are hard-coded values that appear directly in the code. They can reduce code readability and make it challenging to understand the intended purpose of these numbers. Furthermore, changing a magic number might require modifications in multiple places throughout the code, increasing the risk of errors. Using named constants instead of magic numbers enhances code clarity and maintainability. Declaring constants with descriptive names provides context and makes it easier to understand the purpose of the value. This approach also simplifies updates and refactoring, as only the constant needs to be modified, reducing the risk of introducing errors. Using events in Solidity for logging. Events in Solidity are a powerful mechanism for logging critical actions and state changes within your smart contracts. They allow you to record and track important events, providing valuable insights into the execution and behavior of your contract. This information is incredibly helpful for debugging, auditing, and monitoring the state of your smart contract. The provided code demonstrates the use of an event called transfer within a contract called event logging. When a transfer function is executed, the transfer event is emitted, recording the transaction details. This information is accessible through a block explorer, allowing anyone to verify the occurrence of this transfer. Implementing circuit breakers. Circuit breakers act as fail-safe mechanism to halt contract operations in urgent situations. They help mitigate potential damages caused by bugs, vulnerabilities, or unforeseen events. A Boolean variable can indicate the circuit breaker status, with a modifier to restrict access when the breaker is engaged. The provided Solidity code demonstrates a basic implementation of a circuit breaker. The stopped variable indicates the current status of the circuit breaker. The stop in emergency modifier is used to prevent function execution when the circuit breaker is engaged. The owner role can toggle the circuit breaker using the toggle contract active function, ensuring that only authorized personnel control the emergency stop mechanism. Avoiding dependence on block timestamps. Block timestamps can be manipulated by miners, especially in private or permission blockchains. Relying on block timestamps for critical operations can lead to vulnerabilities. It's crucial to avoid depending on timestamps for sensitive operations. Instead of relying on block timestamps, consider using alternative approaches like a random number generator or a decentralized oracle. These methods are more secure and less susceptible to manipulation. Additionally, implement strong validation checks to limit the impact of potential timestamp manipulation. The example code demonstrates a function isValid that checks the current block timestamp is a multiple of 15. This highlights the vulnerability of using timestamps directly, as such checks could expose your smart contract to manipulation. Access control mechanisms. Access control mechanisms are essential for the security of smart contracts. They restrict access to sensitive functions and data, preventing unauthorized modifications or manipulations. OpenZeppelin's Ownable library provides a simple and effective way to implement ownership-based access control. Role-based access control allows for more granular control, assigning roles and permissions to different accounts. The provided Solidity code demonstrates the implementation of an access control mechanism using OpenZeppelin's Ownable library. The restricted function is marked with the only owner modifier, restricting access to only the contract owner, preventing unauthorized actions. Proper error handling. Error handling is a crucial aspect of smart contract development. It helps to prevent unexpected behavior and maintain the integrity of your contract. Solidity offers a range of error handling mechanisms, including require, assert, and revert, each serving specific purposes. The provided Solidity code demonstrates the use of require and assert in a divide function. Require here ensures that the denominator is not 0, preventing division by 0. Assert confirms that the result multiplied by the denominator equals to the numerator, indicating a successful division operation. Ensuring upgradability. Upgradability in smart contracts allows you to modify contract logic without requiring a full redeployment. This capability is crucial for addressing vulnerabilities, adapting to changing requirements, or improving functionality. Proxies and delegate calls are common methods to facilitate upgradability while preserving contract state. Some key points of upgradability are implementing proper access controls and governance mechanisms to manage upgrades, and use upgradable proxy contracts to separate logic from data storage. When implementing upgradability, a proxy contract delegates calls to a logic contract, which can be upgraded without changing the proxy. This separation allows you to update the logic without affecting the data. Gas optimization. Gas optimization is essential for smart contract development, as we have discussed before. It aims to minimize the amount of gas required to execute a transaction, leading to lower transaction fees and improved contract efficiency. High gas consumption can make contracts expensive to interact with, potentially hindering adoption and affecting scalability. Some key points for gas optimization are minimizing code size and using efficient data structures, optimizing loops and avoiding unnecessary calculation, using mappings instead of arrays where possible. In the provided Solidity code, the addData function uses a loop to add elements to a dynamic array. By using a more efficient data structure like mapping, gas consumption can be significantly reduced. Regular audits and reviews. Regular audits and reviews are essential for smart contract security. They help identify vulnerabilities and potential risks, providing an objective evaluation of your contract security. You should conduct thorough assessments involving static analysis, dynamic testing, and manual code reviews. Follow best practices and industry standards to ensure comprehensive testing and vulnerability detection. Involving experienced security auditors in a multifaceted approach ensures that your smart contract undergoes rigorous scrutiny, uncovering potential weaknesses before they can be exploited. Secure Ether transfers. Securely transferring Ether is vital for smart contract security. Avoid reentrancy attacks and other vulnerabilities by implementing robust transfer methods. Use the call method to send Ether and verify the success of the transfer with a require statement. Implement proper error handling to ensure transactions complete correctly. The provided Solidity code demonstrates a secure Ether transfer implementation. The send Ether function uses the call method to send Ether a recipient address. The require statement here validates the success of the transfer, ensuring the transaction is completed successfully and preventing reentrancy attacks. Utilizing multi-signature wallets. Multi-signature wallets require multiple signatures for transactions, mitigating risks associated with single-point failures. They enhance security by involving multiple parties in the control of a single wallet, preventing unauthorized access and minimizing the impact of compromised accounts. Some key points here are: record all transaction requests and signatures on the blockchain for transparency and accountability. Use multi-signature wallets for managing funds, deploying new contracts, or executing sensitive actions. The provided Solidity code demonstrates a basic implementation of a multi-signature wallet. The min signatures variable determines the minimum number of signatures required for a transaction to be executed. The owner's array stores the addresses of all authorized signatures. You can pause to read the code. Secure data handling. Properly handling sensitive data within smart contracts is crucial to prevent security vulnerabilities. You should avoid storing sensitive data directly on chain, as it can be publicly viewable. Some key points here are: using cryptographic hashing functions for data integrity and confidentiality. Store sensitive data off-chain using secure storage solutions and implement encryption methods. And use decentralized oracles or external data sources to access and retrieve data without storing it directly on-chain. The code snippet demonstrates a function that hashes data. Hashing ensures data integrity by verifying that the data has not been altered. Hash data cannot be reversed to reveal the original data, protecting sensitive information. Continuous monitoring and alerts. Continuous monitoring is essential for proactive security in smart contracts. It involves constantly observing contract activity, identifying anomalies, and responding to potential threats. Key points for continuous monitoring are: setting up alert system to notify developers of suspicious activity, allowing for timely intervention and mitigation of risks. Using tools like OpenZeppelin Defender for robust monitoring and alert capabilities. OpenZeppelin Defender provides a real-time insight into contract behavior, enabling informed decision-making and prompt response to security incidents. This continuous monitoring helps in early detection of vulnerabilities, preventing potential attacks, and mitigating damage. In conclusion, by implementing these advanced techniques, you can significantly enhance the security and efficiency of your smart contracts. These are all critical practices for maintaining robust and reliable smart contracts. For any further queries, please reach out to us on our Discord server. Thank you.